Let us try to get into the details. What are the type of defects which are possible in a cast product? First is there may be blowhole or pinhole. We know that they result from high gas content. Now, what are their values and all, I will be discussing in details. Gas content means it can be oxygen, it can be hydrogen, it can be nitrogen. Oxygen, hydrogen, nitrogen, these are soluble in liquid steel, but when they come out of the steel, they come out in the form of gas. So, unless their content, solubility content is limited in liquid steel. I have mentioned earlier, how do you reduce soluble oxygen in liquid steel? You have to do deoxidation, you have to do killing. How do you reduce hydrogen and nitrogen in liquid steel? You have to do degassing in secondary refining. So, all these processes control the amounts of solutes, oxygen, hydrogen and nitrogen in liquid steel. If they are beyond certain levels, I will come to that, you can find out to what extent the formation of pinholes or blowholes will be there. Everything depends on the value of these solutes, amount of these solutes in liquid steel at the time of casting. That is why I had mentioned that when you are doing say primary steel making, your dissolved oxygen is as high as maybe 500 or 600 ppm. Now, if you want to cast that steel, your steel will be like a strainer, because so much of oxygen is there, dissolved oxygen, they will all try to come out as gas. Why it will come out? Because the solubility of oxygen is quite high in liquid steel, but much less in solid steel. So, where will it go? It will try to come out as gas. So, therefore, oxygen, hydrogen, nitrogen content in liquid steel has to be controlled before you do any casting, otherwise you will have blowholes and pinholes. So, this is important. This is one type of defect which is there is a possibility. Then there may be crack formation, this is very important. When the solidification is taking place, the shell might develop some cracks. As I was telling, the shell has certain properties. It is at high temperature and finally slowly coming down to the low temperature. So, at high temperature, what is the strength? What is the toughness of the solid shell, whether it is delta, whether it is gamma, delta, gamma, they have different properties at high temperature. So, these are important, whether they can withstand all those stresses, all those pressure, ferrostatic pressure from inside liquid, or at the surface of the solid shell there are a lot of pressures as I mentioned during bending, during straightening. So, whether the shell can withstand those stress or strain, that will finally decide whether there will be crack formation or not in a solid shell. Then there may be a depression on the cast surface. I will come to it later on why depression will form. Depression basically means the surface is not uniformly flat. Certain portions of the surface will have certain undulations, depressions, it is depressed, certain portions of it. So, that is called depression. This is a defect. We do not want that, we want surface should be more or less flat. Then we may have oscillation marks. I have mentioned that unlike ingot casting, continuous casting mold is not stationary. Look at this is the mold. So, this mold is oscillating, is going up and down vertically continuously during continuous casting. I have mentioned why it is necessary, because otherwise there is a possibility of the shell getting stuck at the mold surface, the sticking problem will be there. So, for that you always require mold to oscillate. There is a frequency, at what frequency it is oscillating, to what extent it will oscillate, there is a amplitude also for the oscillation. So, this is very important. You cannot do any continuous casting without any mold oscillation. So, now when you are oscillating the mold, because of the oscillation nature, there will be certain marks, oscillation marks on the surface of the cast product. These are called oscillation marks. If the depth of the marks these oscillation marks are not very high, that means if it is not deep marks, then it is, we do not call it a defect. But if the oscillation marks are deep, then it is a defect, because it can create a lot of problem. If the oscillation marks are deep, then try to understand what is going to happen. Again, let us come back to here. Suppose we have a oscillation marks on this, or in the mold, suppose there is oscillation marks, because the oscillation marks are forming here itself, mold itself they are forming, because the mold is oscillating. So, if the marks are there, that means what happens? There is a air gap in between. So, there is sort of heat transfer change. Heat is getting extracted from inside to this way outside. So, if there is a air gap formation because of the deep marks, deep oscillation marks, so those areas the heat transfer will be relatively less, and we know that what the role heat transfer plays in solidification, because the size of solidification structure, size of the dendrites depends on the heat transfer. If the heat transfer is high, dendrites will be smaller in size, which is desirable. We do not want a coarse structure, we do not want coarse grains. So, that is dependent on the cast structure, the size of the cast structure, whether the dendrites or final grains, they depend on the heat transfer. So, heat transfer is going to be very important here. So, if there is deep oscillation marks, heat transfer is in those areas will be low, the cast structure, those areas will be coarse, which is undesirable, number one. Number two, there might be, because of this there might be cracks under those deep oscillation marks. So, those are undesirable. So, what are undesirables? Blowholes, pinholes are undesirables, cracks are undesirables, depressions are undesirables, deep oscillation marks are undesirables. Fine oscillation marks may be there, that is not a problem, but if it is deep, there is a problem. Then another important issue which is directly related to the quality of the cast product is the segregation. Now, what is segregation? This again I will be discussing in details. Segregation of alloying elements, of solutes. In iron we have carbon, we may have manganese, we may have silicon, we may have phosphorus, we may have sulfur, we may have oxygen, we may have hydrogen, we may have nitrogen, all are solutes. All solutes will segregate during solidification. Segregation means partitioning, because the solubility limit of solid and liquid are different. For all these solutes, solubility limit is solid is less compared to the liquid. So, what happens when solidification is taking place? There is a movement of alloying elements from solid to the liquid. Why? Because the solubility in solid is less, solubility of oxygen, hydrogen, nitrogen, carbon and all these alloying elements will be less in solid compared to the liquid. So, liquid will move from solid to the liquid phase. There is a combination of solid and liquid when solidification is taking place. Whenever solidification starts, this is a phenomenon. Segregation is starting at that point and it will end only when the solidification is complete. So, segregation basically means preferential movement or transportation of alloying elements, all solutes, carbon, sulfur, phosphorus, oxygen, hydrogen, nitrogen, any element you talk about. The extent of solubility is different, extent of movement will be different, and that I will be discussing in details, but there has to be segregation. Solubility in solid is always less than solubility in liquid. So, segregation will always be there. So, hence what is happening? The liquid is getting more and more rich in the solutes. Try to understand what is happening if there is segregation. There will be segregation during solidification. So, the liquid which is remaining is getting more and more rich. So, what is happening? The portion of the liquid which will finally solidify in the later portion of solidification, they are having high amount of segregated liquid, that means they are rich in the alloying elements. So, therefore, there will be more of segregation in those portions. The solid which is forming at the beginning of solidification, they are relatively purer as with respect to the solute contents, but the solid which is forming at the later portion, so they are having more segregation, more impurity. That is why if you look at a cast product, if you look at the section of a cast product, you will find the center portion is most segregated. Center portion has more of carbon, more of all alloying elements. So, we have to be careful about that. You cannot escape this, but only thing is you have certain controls, so that the segregation level is relatively less. Some parameters, continuous casting parameters will lead to less of segregation. So, that is what is important. Now, all these cracks, depression, oscillation marks, segregation, they are dependent on 3 issues, major 3 issues. First, the casting process as such, the specific steel grade as such, or the caster type, as I have mentioned, whether it is a vertical mold or carved mold, that is called a caster type. What is the radius of the caster? All these will finally generate the magnitude and the distribution of the strain. So, caster type of an alignment will give the relatively what amount of strain on the solid shell. Now, what is casting process? We know continuous castings will take place at a certain speed, that will determine to what extent solidifying will take place, what is the movement of the solid shell, how fast solidifying will take place, all this depends on the casting speed. And another important parameter is the superheat, the heat of the liquid which is being cast, what is the temperature of the liquid steel with respect to its liquidus, how much more it is, that is called superheat. This is very important. I will come to it also later on, what is the effects of speed and superheat. These will have effect on the cast structure. Then what is the powder characteristics? Continuous casting, 2 issues are very important. One is the mold oscillation, which is necessary, and there is the powder which are using for casting. You do not have any continuous casting whether you are not using any lubrication. So, lubrication is given by what? Either it is a powder or by oil. Normally for small billets you have a oil, you use oil as the lubricant, but for most of the other cases, even for thicker billets, for blooms, for slabs, for other near net shape casting, you always have powder as a lubricant. Powder will melt, it will generate slag, mold slag, which will get inside, it will get, where does it get in? You get inside the mold. Inside the mold means at the interface between the mold and the shell, it gets inside here. It is melting here at the top, you are adding powder at the top, powder is melting, slag is forming, slag will be just above the liquid steel, and because of the oscillation, that is another important requirement of oscillation. Because of the oscillation, some amount of liquid slag will be pushed inside here at the interface between the mold and the solid shell. That helps in lubrication, that helps in prevention of sticking, otherwise there is a possibility of this solid shell getting stuck on the mold surface, which is not desirable. So, lubrication is an important requirement, it is given either by the powder or oil. These days mostly powder is used as the lubricant, and this powder characteristics means what do you have in the powder, how much of CaO, how much of SiO2, how much of alumina, how much of calcium fluoride, how much of sodium oxide, all these will give you not only what is the melting point is important because the powder should melt and form the slag. So, that is important. The viscosity is important of whatever mold, whatever slag is forming in the mold, what is the viscosity, what is the tension, interfacial tension. If it is very viscous, it cannot penetrate at the surface of the mold. So, this is very important. So, powder characteristics is very important. This will determine the mold heat transfer. Why this will determine? Because the mold slag from here, because of this oscillation, is getting sucked inside here. So, this film, the film characteristic will determine what is the heat transfer here. This is very important to understand. It will give lubrication, it will give heat transfer. So, what is the film's characteristic? How much of heat transfer will, again there is not only the liquid slag, some of the liquid slag will solidify also because you are cooling it. So, there will be initially a solid slag, then there is a liquid slag. What is the relative thickness of this solid and liquid slag? All these are important. They will give you the lubrication, they will give you the heat transfer. So, in the casting process, speed, superheat is important, powder characteristic is important, mold lubrication depends on this. Then mold oscillation and setting, I have told you what is the frequency of oscillation, what is the amplitude of oscillation, all these are important. What type of steel you are casting, oscillation depends on that. Oscillation is not same for all types of steel. So, this is very important. Then I have told you after primary cooling is then the mold. Heat transfer depends on the type of powder, but in secondary cooling, that means below the mold, when you are cooling with either water or you may cool with air mist. So, what is the extent of secondary cooling? What is the distribution? How intense is it? How it comes down? At what ratio it should come down from the top to bottom? This is very important. This is all part of casting process. Now, another important is, I have discussed a bit of it, sub-entry nozzle configuration and submergence. I have mentioned that liquid steel is coming down from tundish to mold through sub-entry nozzle, a refractory nozzle we call sub-entry nozzle. What is the configuration? Configuration means how it is coming out, what is the port size, what is the shape, whether it is circular or it is elliptical, what is the angle of the port, whether it is the steel will come out horizontally or at an angle or the top or the bottom, what is the angle, that is important. Submergence, how much the ACN will be submerged in mold, all these are important, these are part of the casting process. I mean all these will determine how much there will be oscillation, how much there will be what is that called, turbulence in the mold, these are all important. What is the heat transfer, all these are important. So, casting process is important, I have told caster type and alignment is important, then I have told specific steel grade is important. Why this is important? Solidification mode, solidification sequence will depend on the grade. Solid may be first delta, or it may be delta plus gamma, or it may be gamma, and then when gamma forms, whether it forms during solidification stage or after solidification or at the very beginning itself gamma is forming, these are very important, because solid shell, whether it is delta gamma or delta plus gamma, all this will depend, all will impart the strength and toughness of the solid shell. Then sticking or depression tendency is very important. This grade of steel will determine whether during casting process the shell will try to stick to the mold or try to come away from the mold. These I will discuss in details. So, you will come to know there will be two broad possibilities. Some of the grades are, we call it a sticking type, that means the shell is having less strength or shell is so narrow, so thin that it cannot withstand the ferrostatic pressure, it will try to come towards the mold. So, it is called a sticking type. Certain steels, the shell may be slightly thicker or shell may be of higher strength. So, the contraction may be more there. So, it will try to come away from the mold. So, whether it is coming towards the mold or away from the mold will determine whether it is a sticking type or depression type. I had told you the depression is a typical defect. So, in depression type of grades, certain grades are depression grades, you have the surface where there are certain depressions, undulations which are undesirable. So, this steel grade will determine. Then high temperature strength and ductility, as I have told, this is determined by the grade only, specific steel grade. Then what are the trace elements present? This is very important, I have told you, because how much of sulfur, phosphorus, boron, aluminum, nitrogen, why these are important? Because this will generate segregation. All elements will generate segregation, but these elements I will come when I discuss in detail, you will come to know why sulfur, phosphorus, boron, these are more prone to segregation, they will give more segregation, and they have problem of defects generation are more, these trace elements. So, a control of these elements during secondary refining is very important. More you have these elements, more is the problem. They not only create segregation, they depress the solidus temperature. Whatever you find from the phase diagram is an equilibrium solidus temperature, but in reality during casting you have to deal with actual solidus temperature, because micro segregation will be there. This segregation will depress the solidus temperature from the equilibrium to the actual value, it is always lower. As I have told, always segregation will be there, always all these solutes will try to be more in the liquid than in solid, which will always happen, and because of that the solubility, because of this increased solubility in the remaining liquid, the portion which is solidifying at the later stage will have more of these elements, and the last liquid which is solidifying, the solidus temperature is always coming down because of this. So, these are all issues which have to be taken care of, which we have to be careful, then only we should have a good cast product, otherwise all these types of defects will come. Now, I will just try to discuss why blowholes and pinholes are created. I have told you here that blowholes and pinholes, they are basically coming from the gas content, this is one type of defect. Now, to what extent we can control them, we will now discuss. Relatively high content of soluble oxygen, nitrogen, hydrogen, I have mentioned this. These three elements have to be properly controlled in liquid steel before you cast. So, otherwise you will be having blowholes and pinholes. So, what is important is adequate deoxidation and degassing. Oxygen you are controlling through deoxidation, and nitrogen and hydrogen you can control through degassing. This I have discussed earlier when I discussed about how to control the all these elements in steel in secondary refining. So, adequate deoxidation, degassing are essential. Now, why there is a problem during casting, let us try to understand. With progress of casting, as I have mentioned, due to segregation, content of solute, oxygen, carbon, nitrogen, hydrogen remaining in liquid steel, this is increasing due to segregation. So, initially whatever content of oxygen, carbon, nitrogen, hydrogen you have started in the liquid steel, as you are going ahead with solidification, that means with progress of solidification, the liquid steel is getting more and more rich, more and more segregated with oxygen, carbon, nitrogen, hydrogen and all these elements. This is related to segregation. So, what is the problem if this all increases? First, the base level is important, but from the base level also we are getting more and more of this during the course of solidification. First, the base level has to be low, that is first thing, then only whatever increase is there will be within a certain limits. Now, we know, I think we have discussed with this, that hydrogen, nitrogen, oxygen, these are coming out of liquid steel rather in solid steel, like whatever hydrogen is there in liquid steel during solidification, it will come out as gas. So, it come out as what? Gas. So, this is from the reaction you can know hydrogen which is solute in liquid steel, when it is coming out of liquid steel in solid in the form of a gas. So, from this relation, this is the constant. So, from this is fixed for at a particular temperature. So, at a particular temperature we know what is the amount of, suppose we know amount of hydrogen, this is the Henryan activity. We know that hydrogen, nitrogen, oxygen, these are very present in a very low amount in liquid steel. So, we can take Henryan activity as equal to the percentage or ppm of these elements or percentage of these elements in liquid steel. So, Henryan activity is equal to this constant into partial pressure of hydrogen to the power half. That means, if we know this, how much of hydrogen is present, we can, this value is known from the thermodynamic properties. So, we from this reaction we know at a particular temperature this is fixed. So, we know what is the partial pressure of hydrogen for a particular value of hydrogen. Similarly, for nitrogen we know what is the partial pressure of nitrogen. If the partial pressure of hydrogen and nitrogen are more, partial pressure of nitrogen, hydrogen also will be more, because this is in equilibrium with this is fixed, this is more, solubility is more, we have more of partial pressure of hydrogen, solubility of nitrogen is more, we have more of partial pressure of nitrogen. If the solubility of carbon and oxygen is more, multiplication of this, partial pressure of carbon monoxide will be more, because this is fixed at a particular temperature. So, what is happening? If you have more of hydrogen, nitrogen, carbon and oxygen in liquid steel, you have more of partial pressure of hydrogen, more partial pressure of nitrogen, more partial pressure of carbon monoxide, which is coming out in the form of gas bubble in solid. So, more of this means more of the partial pressure of this. So, what is going to happen? So, first thing is we can calculate from these values what is the partial pressure of hydrogen, nitrogen, carbon monoxide. I think it is clear, because these reactions I have discussed earlier at the time of degassing or decarbonization, I have discussed all these reactions. So, we know these values, hydrogen, nitrogen, carbon, oxygen, we know partial pressure of hydrogen, nitrogen and carbon monoxide. So, total of these three is hydrogen, nitrogen, carbon monoxide is important. This total value, if it is more than the atmospheric pressure and the ferrostatic pressure, then gas bubbles will form. You try to understand what is happening. Because of hydrogen, nitrogen and carbon and oxygen in liquid steel, when you are during solidification they are trying to come out in the form of gas. So, there is a partial pressure of hydrogen, nitrogen and carbon monoxide depending on how much of hydrogen, nitrogen, carbon and oxygen is there in liquid steel. Less is this value of hydrogen, nitrogen, carbon, oxygen, less will be the partial pressures. And if the partial pressures are low, P total is low, total pressure of from these partial pressures is low. If the pressure is low, then it is less than atmospheric pressure and ferrostatic pressure. I have told you there is liquid steel at the time of solidification. When the solidification is complete, then only there is no liquid steel. So, there is a ferrostatic pressure. As you are coming down the liquid steel, as I mentioned, ferrostatic pressure is increasing. Is it clear? When the solidification is starting, ferrostatic pressure is almost nil, because solidification is starting at the top of the caster, top of the mold. As you are coming down, that means solidification is getting more and more complete. At the almost at the end of solidification, this pressure, ferrostatic pressure is high. So, what I have told here is this summation of the three partial pressures should be less than atmospheric pressure and the ferrostatic pressure. If it is so, there will be no gas bubble formation. They cannot form, they cannot come out in the form of gas. So, there will be no blowholes and pinholes. Is it clear? So, what is the secret of restricting blowholes and pinholes? You have less amount of dissolved oxygen, less amount of dissolved carbon, less amount of nitrogen, less amount of hydrogen. Carbon, of course, okay, carbon and oxygen are interrelated. If you have more amount of dissolved carbon, your dissolved oxygen will come down. So, carbon is of course something related to the what is that called, your chemistry of steel. Okay, forget about carbon, but you should have less amount of dissolved oxygen, less amount of dissolved nitrogen, less amount of dissolved hydrogen. So, if you have less amount of this, partial pressures of hydrogen, nitrogen and CO will be less, total pressure will be less. So, it will be less than this. So, there will be no blowholes and pinholes. So, please remember the secret of having no blowholes and pinholes in liquid in cast product when you are continuous casting from liquid steel to either slab, bloom or billet, whatever it is, or even during ingot casting. This is true. This is in principle true for everything. But only thing is ferrostatic pressure here, it is increasing at the end, towards the end of the continuous casting here, towards the end of continuous casting certification. So, we have to remember this relation. Total pressure of these three partial pressures, hydrogen, nitrogen, CO, has to be less than atmospheric pressure and ferrostatic pressure. In that case, there will be no blowholes and pinholes. If you have more of hydrogen, nitrogen, oxygen means more of partial pressures. So, the total pressure will be more, and if it exceeds, total pressure exceeds the summation of atmospheric pressure and ferrostatic pressure, you have blowholes and pinholes, so which is undesirable. So, as I have mentioned, the first requirement of a good cast product is absence of blowhole and pinhole, and for that we must have low amount of these contents. We must do good deoxidation, we must do good degassing to take care of hydrogen and nitrogen. This is the first requirement. Then only you have absence of blowholes and pinholes. I have tried to explain what is the principle, why does it form. I think we will next discuss, maybe in subsequent lectures, how the other defects are generated. Thank you very much.